Aloha, Rich Halverson here. This is ITS148, and today is March 9th, and we're gonna have two classes this week, and we're gonna talk about recursion. So this class, I'm gonna go through chapter 14, I think is what it is, and explain recursion, and then your assignment, which I haven't quite finished posting it, but I will tell you exactly what it is, and I'll make points about it throughout the class today, it is going to be. I'll tell you what. I'll share my screen and show you. And the reason I'm doing this way is because for those of you that are just tuning in, can I put this transcript thing over here? I don't think so. I guess I can't put it on my shared screen, or I don't know, maybe it shows up there anyway. Anyway, all right, so we're in 148, and this is the syllabus, and we are behind because I think we're like a week behind. Today's the 9th, and we should be finishing this chapter this week. So I guess I'm just like 1 week behind. But I am going to touch a little bit on analysis of algorithms too, because the assignment is what's called a NP complete problem. It's a traveling salesperson type problem. It's figuring out all the combinations of a path. Combinations of visiting all of the nodes of a graph, for example. There's lots of problems like that, and we are now getting into standard algorithms that every bachelor's degree in computer science person should know. We get more into that in 228, but it's basically things like sorting, and then it's how you manipulate trees, how you use binary trees to help you do things, and then graphs, how you use graphs to help you do things, and it's traversing through them or visiting all of the nodes or those kinds of problems. All right, so if we go to chapter 5, or chapter 14, I'm going to talk about recursion, and then this next assignment is going to be to do a problem like this lab that I think we're going to be able to get to today, and you have to implement it, and you have to use. I would like you to insert the print statements like you do in this section. So this is putting in print statements to help you debug your recursive program. And recursive programs call themselves, so they can call themselves a bunch of times. So you kind of nest, you get this nested thing, and you nest down, and then there's got to be something to make it stop calling itself. And that happens, and then it comes back out again, and it's interesting to see that, because you can put in print statements to indent where the depth of the indent is the depth of the indent is the depth of the recursion. So this it calls the function here, and then the function calls itself again here, and the function calls itself again here, and determines if the person cannot be found. So then it returns out, and then it's done. It says person is not found. Anyway, so let's go through this, starting with section 1. So the lecture from now on is going to be, if you'd like to hear me go through the chapters of the book, but I think I've given you the important things of what's going to be in this lecture. So if you learn better by not hearing me talk and reading and going through the exercises yourself, then now you can start doing that. I'd like to go through these because recursion is always one of those things that you have to remember how it works, and your mind has to think a particular way that you don't normally do in everyday life. And so it's almost kind of fun to do that. All right, so a recursive function, a function may call other functions, as you know, but a function can also call itself. A function that calls itself is called a recursive function. Now the function doesn't have to call itself directly. The function can call another function, which calls another function, which calls the first function. That's also recursion. So here we have an example, a very simple recursive example where you start out, it's a program, and you start out, it's a little function with an argument of 2, comes in here, and what this does is if this number that comes in is not 0, then it takes the else case, and the first thing it does in the else case is it prints the number out. Okay, then it calls itself, but it calls itself with the number -1. So calling itself comes back around, starts executing, but the number is less by 1. Is it 0? No. Then it prints it again. It keeps on going until eventually, because you're going down by 1 each time, eventually this is going to hit. And once this hits, then it prints out go, and then it returns, and then it keeps on returning to the point after the point it was called, but there is no point after the point it was called, so the method is done. So it continues to return until it hits the first time that it was called. And I'm gonna do some little examples here to help you see this, because it's not quite obvious to everybody, I think, this concept of you call a method, and then when the method is done, you start with the statement immediately following the method, and if it happens to be, the method is done now and it quits, so then that causes the return. So I tell you what, I'm going to take this little program here, and I'm going to copy it into my test, and I'm just going to run this. This is my test program, and so I can do test. I'm at my desktop. That's this program, and you see it starts out with 2, and then with 1, and then it says go, just like it said here. Now, what I'd like to do is say, okay, right here, what's going on? These spaces. Now they are spaces, good. So this is a terrible editor. I don't have it set up right for Python. Print. I'm back from count down, parentheses, quote, comma, and I'm just going to print this out. Oh, cool. Should be, I want this to be, forget it, I'm not going to mess with these parentheses things. Okay, so so I don't need this. So I put this here because when this runs, I want you to see where it calls and then where it comes back, and how it eventually pops out of the, pop as in stack, pops out of the calling sequence. So I'm going to put that here, and I'm going to put this here. Okay, now call, I'm going to say now call. Okay, so let's see. So first I print out the count, and then I say what I'm going to do. I'm going to call this, and I do it, and then I come back. And so let's watch this one, and let's make this a bigger number. Let's make it like 5, so we can see it a little more. All right. So if I go like this, we see 5, and so it prints out the 5. It prints out the 5, and then it says now call countdown 4. It prints out the 4. Now call countdown 3. Now call countdown 2. Now call countdown 1. Now call countdown 0. And look, it has never gotten here yet. It only just goes, you know, here, 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 and then back here, 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 and back, and keeps on. It goes all the way down until count reaches 0, and then it starts coming back. So it hits go, and it returns, back from where it says not call countdown 0, which is when count is equal to 1. So when this is done, it returns, and it returns to the particular instance or call of this program. It's called, it looks like 5 times. So it returns back to the maybe it's called 6 times, and then it returns back to the previous one. I'm back from calling countdown of 0, and then immediately I'm back from calling countdown 1. I'm back from calling 2, 3, 4, and then the program ends. So now recursion, recursion is like this. The recursion can either be where you do what you're going to do before you call yourself again, or you do what you're going to do after you call yourself again. Okay, in this case, we're doing what we're going to do before we call ourselves again. Okay, we're printing ourselves out, we're printing out our value, and then we call ourselves again. So this I don't know what the term is, a front recursion, rear recursion, back recursion. I'm not sure what the term is used in this textbook, but just keep that in mind, especially later on, because recursive programs are the best for visiting all of the nodes in a tree. And you may want to visit all the nodes in different search orders. You reach the node that's a tree, and you're either going to print the node you're at, then go to the left node, and then come back and go to the right node, or you're gonna go to the next node first, and then when you come back, you're gonna print, go to the right node, or you're gonna print yourself at the very end. And that particular knowing how to traverse trees in those 3 different ways helps you solve all kinds of problems in computer science. And we may get to some of those later. Anyway, so that's an example of a recursion. You call itself. And so now you can do these programs. This looks just like the same. This looks just like the one that we just did. And so here this is supposed to, you enter in a letter, and then it prints all the letters backwards down to the lowercase, down to A. Well, that looks just like this one, okay, except for we're counting down. So that would just be something simple like, and I'm just going to do it here for you just to see if I got it right. You just have to call backwards alphabet, and it's going to be the starting letter that you're going to call it with. Okay, so we're calling it with that. And so it comes in, and is the current letter that we're looking at an A? Well, I don't know. If it's not, it skips and prints it out, and then it figures out what the ordinal or the ASCII value of that letter is. For A, I think it's like 90 or some 91 or something. Let's see where it is. ASCII values. Network. Here's one. Here's a nice ASCII. there's a table. Can I look at one? I don't want pictures of one. ASCII table. Okay, so oh, here we go. The letter A is the value 97. So it's like we type in an F, and that's 102. That's an ordinal 102. And so here we figure out that that's 102. We subtract 1 from 102. That makes it 101. What's the character of 101? Well, the character of 101 is E. So so now we're calling the method again, but not on F, but on E. And next time it's going to be D, and next time it's going to be C, and then B, and then once it's A, it doesn't call itself anymore. Then it starts returning, just like in the example I just showed you. So so let's run this. It's right. It's correct. Well, we know it's correct. But so what's interesting now is let's run this again. Yeah, let's. Oh, wait a second. Can we? Oh, it doesn't let you. Okay, so let's run this again. Okay, here it is. And but this time let's actually execute this. Enter number. So I know what I'm doing. And so now when we run this, okay, enter a number. What happens if we enter a number? Okay, A, something up here goes down to A. What happens if we enter a number that's enter a letter that's already underneath A? Okay, well, it should go all blah, 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 and then I don't know what's going to happen when it gets down here. I think this gets to some character that it's not allowed to print or something, and it dies. So let's just see what happens when I do that. So I'm going to enter. No, I shouldn't be entering a number. I should be entering a letter. Sorry. Enter letter. I'm going to do capital F. Doesn't look right, but look at that. So it starts printing everything out. It starts printing all the down, and then it starts to print an @ sign and it starts to print an @ sign. Then it starts to print question mark, greater than sign, blah blah blah, 98765432210, all the way down to whatever. It's down here, and here it's printing out funny characters, but really we're down into these special, line feed. By the way, this is backspace. No, this is line feed or new line, and this is carriage return. So these are characters that we see all the time. In fact, these can mess you up if you don't use them right. But anyway, so it gets down to the point where, okay, it was repeated 67 times. That makes sense because F is okay. So it must have gotten messed up around here because it only went 67 times. Value error, character argument is not as okay. So the character. Oh, okay. So this is 0. Okay, so this is a particular range. This is a hexadecimal. I mean, this is a binary number. But anyway, the character function. I sent the character function an argument that was out of range. So there was a value error because this ended up being out of range. It could have ended up being 0 or something, or -1. There's no, you can't have -1 because why? Because it never hits. It never hits there. So it keeps on going. So this is a problem with recursive algorithms, where if you make a mistake and it never hits the stopping point, then it just goes forever, and there are limits. Then you run into the limits of how many times you're allowed to call yourself. And I think the default is like 1,000 times, you know, but so once you hit 1,000, but this stopped because of the argument error. All right, so anyway, that's section 1. Let's keep on moving here. So there's the binary search algorithm. Binary search is a very good example of how you can implement something recursively. I don't think we've come to searching and sorting yet, have we? Search, okay, search. Oh, that comes next chapter. We'll get into this more deeply. But the way of oh, okay, nice. This is okay. So, what's an algorithm? Well, an algorithm is just a sequence of steps for solving a problem. So, you know, this is an algorithm for making lemonade, and this is an algorithm for mowing the lawn. Mowing the lawn is recursive because first you mow the lawn. To mow the lawn, first you mow the front yard, and then you mow the backyard. And mowing involves mowing. You know, so anyway, you could write a recursive algorithm for mowing the lawn. It looks like for the binary search, it's a well-known algorithm. First of all, everything's got to be sorted. So let's say you're looking for a number like 32, and it's sorted. And so first you know how many of them there are. In this simple example, we're just going to assume that there's 100 numbers, but it wouldn't have to be 100. There could be missing ones. And so first of all, you say, okay, I'm searching for the number 32. Well, what's the, remember it's sorted. What's the number exactly in the middle? Well, oh, look, it's 50. 50, that's the number exactly in the middle. Well, now I know that 32 must be on the left side and not on the right side. So we know 32 is over here, okay? Okay, so we've already eliminated half of them, okay? And then we have from 0 to 50, and we say, well, what's the number right in the middle? It's 25. Oh, 25. Well, 32 is bigger than 25. So that means that 32 must be on the right side and not the left side. So we've already cut it down by half again. Each time we do this, we're cutting the number of elements that we need to look at by a half. You know, we hack off a half until we finally reach either one element or no elements, okay? No elements would mean that the 32 is not in there. Finding one element would mean we actually find the 32. We find what we're looking for. And so you can write a recursive algorithm where you give it the range. You say you start with 0 to 100. Look for 32, and it's going to find it. So it's going to start with 50, and it's going to go. Oh, it's in the lower half. So then it calls itself again, but this time between 0 and 50. Okay, so and then it calls itself again, but the next time it would be between 25 and 50. So the arguments, the parameters for the recursive function would be the range that you want to search in, and then the number that you're searching for. And that's what this is. So this is the recursive find function carrying out the binary search algorithm. So first of all, we come in and we have a low and a high, and the first time this number is called, the first time this one is called, it's with the full range. This implements exactly this up here. And then so we start out with a 0 and 100. This figures out the middle one, which is going to be 50. And then is the number we're looking for less than or greater than or equal to? Well, it could be equal to. Oh, is this the number? And you're either going to answer it's lower or it's higher or it's equal to. Yes. So if it's not lower or higher, this is testing. If it's not lower or higher, it's going to say, it got it. And if it's lower, it calls itself again. The low parameter stays the same, but the high parameter is going to be, because it's in the lower half, the high parameter is going to be this mid here. Whereas if it's in the upper half, the low parameter is going to be mid plus 1, and the high parameter is going to be what the high was here. And it keeps on calling itself until it either got it or it didn't. Okay, this is a sort of a manual thing. You're going to have to answer truthfully each time. All right. So recursively searching a sorted list. This is how this is modified a little bit so it actually works. So there's a range size. You figure out the mid. This is in this example, it looks like we have a sorted list of people, and we are looking at. Oh, we're searching the list to see if we can find the person, and it's. You notice when we create the list, we create it in alphabetical order. So it has to be sorted, which is why searching and sorting are usually taught together. First, we teach searching, we realize the importance of sorting, and then we study all the different ways you can sort. Lots of different ways to sort. There's a lot of different sorting algorithms. This looks at first item, finds the index of a string in a list of strings, searches only the index range low to high, upper and lowercase characters matter. So if the item is less than, first must be our list. Oh, this is the list. This is this thing. This is this thing. It's this. Okay, so this is the list. This is the item we're looking for, and this is the range. These are indexes. And so, I wonder what the purpose of calculating range is. Oh, we know if we're done. If low and high is equal to 1, then we know then we know it wasn't found. If after we calculate mid, that's the item, great, we found it, and we just return. Otherwise, it's going to be, if it's in there, it's going to be either less than mid or it's going to be greater than mid, in which case we call ourselves again. We are returning an index. See, we return. Wait. Oh, here. See, we figure out the position, and then that's what we return. So anyway, that's and we see that's recursive. It's interesting. We're learning these this algorithm. It seems did we cover it in the previous? We must have covered it before. Of course, there's the non-recursive version where we just basically do the same things, but we don't call ourselves. We have a loop, a while loop, and each time we iterate through the while loop, we're changing mid, we're changing high, low, and mid. We're changing mid every time. Then we're changing either high or low, and then we iterate through the loop again, and we end up finding the same answer. Really, recursive programs are not any more efficient than the non-recursive versions. Than the iterative, they're either an algorithm, like for example, this would be either iterative or recursive, and recursive programs are not any more efficient. They're just more elegant. They're more smaller solutions, and maybe they're easier to prove their correctness, and and in some cases it's substantial, so that's why we do it. There are cases like the processor, like when you type in your Python program, or when your Python program is there, the little algorithm that goes through and makes sure that the syntax of your program is correct. That's probably a recursive program, because especially with expressions, you can nest expressions inside expressions, and that's those kinds of problems lend themselves to recursive algorithms. All right, so adding output statements. Okay, so this is the important part, where debugging recursion. So I would like you to do this for your next assignment. So you're going to take an algorithm that where you can pretty much, I mean, all the trouble with these assignments these days is anything I give you, you can probably search the internet and find the solution. Find the solution to the basic algorithm. So what I'm going to do is take these basic algorithms. You can find them. I might even tell you where to find them. Or they might be taken right out of the book. And I'm going to ask you to do a little bit of a modification thing. So just so you understand, it shows that you understand what the algorithm, how the algorithm actually works. All right, so and here, this helps you debug. Okay, so here we're gonna this program, it's the same find program where you give it a list, something you're looking for, and a low and a high, but then you're also including this indent number, which which each time you call find, you're including this indent number, but each time you call, you add some extra spaces to the indent. So it's not a number, it's actually a bunch of spaces. So the first time you run it, it's here, it looks like. So you call this find program, and the indent is 1, 2, 3. Yeah, 3. The indent is 3 spaces. And you notice it's the full range from 0 to the whole length of the list. And we call it, and this is the list. And it comes in, and we print out what we're doing this time. So that's this, we're printing out. So here we have a list of folks, 5 people, and we're going to search for somebody. Does it have to go both this? Oh, well, we're searching for something that looks just like that. We aren't gonna first search for the last name and the first name. We're searching for something exactly like this. Okay, so we got these 5 people, and it's sorted, it's alphabetical. And so each time we call ourselves, the first time we call, we just pass in 3 spaces. The indent is 3 spaces, 3 spaces. But you see, once we enter, we print out this. We print out find this range, the low high, and then it goes and does it. But sometime in between here, it may call itself again. And here, if the item we're looking for is below the mid, then the low is going to be the same, but the high is going to change to what the mid is now. And then we're going to add 3 more spaces onto this. Just 3 more spaces onto indent before we call ourselves again. And or if it's, of course, if the item we're looking for is bigger, then then the low changes to mid +1 and the high remains the same. And we add 3 spaces. So each time we come in here and we print this out, this is the only place we print indent. We print it out, and that's what these spaces are in between here, and then here, and then here. See, so we see that that find was called once by the main program, again by itself, and again by itself. And then after that, it has to return, it returns, it returns, it returns. So down after the third one, it realizes that, see, range is 4, 4. So the range is the item is not equal to, we calculate mid, and the range would be itself, because low and high is the same. So mid is just pointing to the same thing. If that's the item, we found it, we return the value. I know we set pos equal to value, and we end up returning. Here we return it. Or if the range size, if this fails, but the range size is equal to 1, high minus low plus 1 is high and low are the same, so range size is equal to 1. If range size is equal to 1 and this one fails, which means it's not in there, then we know that the person is not in here because we've exhausted the search. So that's when we return the -1, or we set pos equal to -1. So this is the only place where pos ever gets so after this and after this are the only two that we don't call ourselves again. So it's after this and after this, that drops right down to here, and we output that, and we output that. And then of course, when we return from calling ourselves, we're going to be down like right here, right below this one, because this was the, or right below this one. So anyway, so I'd like you to use this and there's going to be some recursive program. It's going to be this. I'm going to do something similar to this all permutations, because all permutations is what's called an NP complete problem, which is an important class of problems in computer science. All right, so so let's keep moving here. So that's how that works. Let's what am I supposed to do here? Enter some name. Smo Joe. All right. So it did the range 3 times. So I'm just going to do, what time is it? 7:25. I'm just going to go, how far are we? All right, I'm going to keep moving here. I'll come back to more of that when I explain the assignment next time. So for creating a recursive function, and I'm going to probably have you create a recursive function sometime this semester. By the way, there's going to be to see how well I am teaching the learning outcomes for this course. I'm going to have you do some little quizzy type problems. They're not going to be worth hardly very much at all towards your grade. So in other words, you can bomb on them completely and still get an A. But I'd like you to try as hard as you can to do them, and I'm going to use those scores to assess my success at teaching the class. Teaching the aggregate class, not you individually, but the aggregate of the class, certain concepts that you're supposed to learn out of this class. So anyway, and writing a recursive function, I can't remember if it's this class or the 228, but something like this, anything like this. And in fact, this is how it is for computer science classes, past the first couple courses, where really all you're doing is figuring out which technique you learned to apply to certain problems, and the solutions are usually quite short. It's figuring out which certain algorithm applies to the problem you're solving, what the best one is. So it's that kind of thing. Here it's the technique of writing a recursive function. So it could be a very bogus recursive function, some function that you'd never write recursively anyway, like listing all of the letters from some letter back down to A. We wrote recursive versions of that, but of course you would not do that. You would write an iterative version. You would write an iterative program to do that. So anyway, when you write a recursive function, you have to write a base case, and a base case is the thing that ends it. It will return a value without performing a recursive call. Programmer may write that part of the function first at the top and test it, make sure that there could be multiple base cases because it comes in, and in binary search, we noticed in the last one to find there's two base cases. And then you write the recursive case where the programmer adds a recursive case to the function where it's calling itself. And it should call itself with new parameters that will eventually lead to the base case. So this illustrates a simple function that computes n factorial. So the base case is when n equals 1, which evaluates to 1. So when it comes in, if n is equal to 1, then it just returns 1. Otherwise, it takes, let's say it's 5 factorial. It takes 5 times n factorial of 5 minus 1, which is 4. So this is the solution, but you see here we're calling ourselves, and so we keep on calling ourselves, and we end up really it's 5 times 4 times 3 times 2 times 1, and that's what n factorial is. And we can write, again, it'd be easier to write an iterative algorithm to solve this, but it's a nice algorithm to teach the concept of recursion. So this is the recursive part. This is the base part, and so factorial is not necessarily good. Factorial is not necessarily a good candidate for a recursive function because a non-recursive version using a loop is so simple. However, okay, so that's just says what I just said. Typically, recursion is useful for dealing with data structures of unknown size and connectivity. Properties most commonly associated with tree-shaped data structures. So we will be getting into trees down here at the end of the semester. And 228 spent a lot of time on trees, all different kinds of trees. All right. So here we see for n factorial, it's the base case is n equals 1 or n equals 0, possibly. Otherwise, otherwise we return. This is here we're just putting in the base case, and we test it. Yeah, all good, it works. Then we put in the rest of the case, the else. Else is not a base case. This is the recursive case, and we put that right there. So that's pretty straightforward. And make sure you click through all these, so you get all the points. Computing n factorial does not have a natural recursive solution but a recursive solution is not better than it does have a natural recursive solution, but the recursive solution is not better than the non-recursive ones that simply uses a loop. Binary search is a natural recursive solution, and that solution may be easier understood than a non-recursive version. Yes. But you can take any recursive algorithm and rewrite it as a non-recursive algorithm. All right, so a common error is not to cover all possible base cases. Another common error is to write a recursive function that always doesn't reach the base case. Both errors lead to infinite recursion, and the program will fail. Commonly, we use two functions. We have an outer function, which is the first thing that calls the inner function, the recursive function, and then the recursive function will call itself a bunch of times. The inner function is intended only to be called from the outer function like this. The outer function may check the validity of the input value and so on. All right, recursive function, writing the base case. Okay, add an if branch to complete double pennies base case. Sample output is, okay, number of pennies after 10 days. So we're supposed to enter 1 and 10. If the submitted code has an infinite loop, the system will stop running the code after a few seconds and report program end never reached. The system does not print the test case that caused the error message. All right, so what is this? I don't even know what this program is supposed to do. Number of pennies. Oh, we start with a number of pennies, and there's a number of days. Okay, so we start with a number of pennies, and we're supposed to write the base case. So total pennies. Okay, so it looks like the number of days goes down, and the number of pennies doubles. So print the number of pennies, double pennies, starting pennies, user days. Why does it say? Okay, anyway, so my solution would be something like, I guess, what's the base case? If num days equals 0, return total pennies equals num pennies. Okay, I'm gonna see if this works. Otherwise, we're gonna double it, and I don't want to. I want to. What is this? Well, this is a second challenge. All right, I want to test this. I want to do it better. I'm going to copy this, put it here, and let me just, where am I asking something? Starting pennies. And this is num days. All right, what does this do? Okay, so and what was the, oh, 1 and 10 should equal 1024. So let's run it. Now starting pennies 1, number of days 10. Oh, okay. Well, looks like I got the right answer. It's that easy. See, it could have been 1. I wasn't sure if it was 1, and I wasn't sure if we're supposed to return 0, but no, that would make sense. No, that makes sense. Okay, so what are the other possibilities where I could have made a mistake? What happens if I put a 0 here? I'm just going to see what happens. 1, 10. Oh, never mind. 1, 10. Okay. It's because it gets back 0. Oh, it's always going to get back 0. Each time it's going to get back 0. So this should be num pennies. You should make sure you see this in your mind. And the other thing I was wondering is, could this be 0? Can this be 1? What would happens if it's 1? Probably we end up short by 512. Yeah, 512. So we're 1 day short. All right, so it should be 0. One. All right, now make sure when you do it, you don't have anything in here. Make sure that's not it. You don't put anything in there. No, wait a minute. No, of course you don't. You just put in the base case. All right, this one. Factorial. Output string, next counter, next value. Okay. I'm just gonna take a wild guess. Wait, what is it supposed to? Okay, I'm gonna copy this over again. I'm gonna leave it for you to put it in here correctly, but I'm just gonna kind of work with patterns here. And this is, after a while, you don't really have to understand completely, you just kind of figure out the pattern. And so we got to put something right here. And that's where the recursion part is. And we're calling this. So I'm sure it's this. I got to put, I'm going to put factorial string, parentheses, and then the counter is probably next counter because it's decremented. So we're going down. We're going down. This is going down to 0, or it's going down to 1. This thing is the decrementation, or the reduction of by 1 of thing coming in. So I bet you that's the first one. Next counter. And I bet you that the value is next value. Just so multiply, because of factorial. So take next. Okay, yeah. All right, I'm going to put next value here and see what here I get. And then I'm going to run it. And what's the input supposed to be now? 5. Whatever. So let me, this class is almost done, isn't it? Let me run this. And what happens if I put in 5? We get, all right, looks pretty good. I guess I was right. So anyway, you can put those in. Where are we now? 4, 5, recursive export. Oh, recursive explanation. Okay, so this is this NP. Okay, so this is this NP complete problem I was telling you about, where you try all possibilities. It's trying all possibilities, and there's certain problems where to find the solution, you gotta test all the paths. So let's say you have a traveling salesperson, and the person's starts out in a city and has 5 other cities that the person has to visit, and wants to find the cheapest airfare to be able to visit all these cities. So it would, let's say you have, all the cities, and the distance between the cities is the airfare. And so and so each of the connecting cities, the airfare is going to be different. Maybe, probably could be different. And so what you need to do is find the shortest path, or find the cheapest path to visit all 5 cities. And so it's going to be either this way, this way, this way, or this, who knows? It's probably not related to distance. It's related to something else. So that would be an example of where you just have to try out possibilities. There's no faster, trickier way to figure out what the cheapest path or the shortest path is. And in fact, if you were to find a faster, cheaper way faster way to do it, other than trying out possibilities, you'd be a millionaire, billionaire. You'd be famous. But they have, or if you could prove that it's impossible to find a faster algorithm, faster than trying all possibilities. If you could prove that it's impossible to find, also you'll be famous, okay? Because they haven't been able to prove that we can't do it, but they haven't been able to prove a solution to it. So those are NP complete problems. This is an example of one, exploring all possibilities. So let's say you have what you want to you have A, B, and C, and you want to figure out all the possible combinations of those three letters. And so what you do is you start with the for each, anyway, there's an algorithm for this, and this is what the tree looks like. And but when we're all done, the bottom, I think this is all the possibilities right here. And so it's generating all these. Scramble the words, letters in every possible way. This is an example. Where we have to, we have like a list of the letters, and we start out, we take the first letter, and then we add to that every possible combination, or every possible permutation of the remaining letters, and so on. Anyway, that's the algorithm. This is the algorithm. It's the end of the class now. And so you can look through this, try to click. Is there anything to click through? Yeah, there is stuff to click through. Click through this. We can go through the challenge. Let's see, what time is it? I think we're supposed to go through this. Anyway, it's 11:45. I'll probably start here next time. And so next class, I'll go through this, finding all possibilities recursively, go through this algorithm, and introduce you to, and that's what this permutation of names is, and then the Fibonacci sequence is similar to what we did earlier. So that's it for today. That covers the lecture chapter on recursion, almost. Yeah, you got any questions?
Oh, thank you, Dr. Harrison.
Oh, okay.
Yeah, I'll just, yeah.
Right. Good. Thank you. We will see you maybe next time.
Okay. All right. See you later.
Thanks for watching. Yep. Bye.
Bye.